So let me just start by saying that this is a tutorial, which means that you can ask questions during the talk, and also I don't have any fancy videos. So let's start. So this is my selling slide, but after yesterday, I don't know how much I have to say. I was really impressed with everything that's happening on quantum networks. So I just want to say one thing, that yesterday from the beginning to end, we were talking about QKD. And QKD is fantastic. But you can only use QKD when you have two agents in a network that they actually trust each other. What they don't trust is the communication between them, the communication channel between them. And in this case, you can actually do QKD and then start communicating in a secure way. But many times this is not enough, because imagine that you want to use your credit card online to pay for something on a website. You don't necessarily trust the website, right? Or imagine that Google, after 5 years or 10 or 20 years, they say, we now have a quantum computer, so give me your data. I will do some processing, some computation on my quantum computer, and I will send you back the data. Again, you don't want to trust Google with your data, right? You want to do things in a secure way. So when we're talking here about quantum networks, we're talking about a network of agents. Some of them are classical, some of them are quantum. And what they want to do is they want to do some kind of tasks, some distributed tasks. They don't trust each other, but they still want to have some security, okay? So here we'll be talking about a network of agents that they don't trust each other, okay? And we want to see if quantum information can actually achieve some security in this model. So let's see. All right. So there are some fundamental primitives that we have in this scenario, in this network of distrustful agents. So some of them are, for example, coin flipping, bit commitment, oblivious transfer. I will be talking about all these kind of primitives. The reason we're talking about these fundamental primitives is that many of the more difficult things that you would imagine trying to do, like paying with a credit card or identifying yourself or doing things like electronic voting, this kind of thing can be reduced to this sort of fundamental primitives, okay? So if we know something about the security of these fundamental primitives, we could potentially say something about the security of more elaborate operations in the network, okay? And of course, if we don't know how to prove security for these very simple primitives, then it's kind of difficult to start asking about security in more difficult situations. And I will also be talking about different security models. So the first model that we'll be talking mostly in this talk will be information theoretic. Well, why this is kind of what we claim that quantum information is good for, right? This is why QKD is fantastic, because it can give you information theoretic security, while classically you can always only have like computational assumptions, computational security. So I will try to understand what kind of primitives we can do with information theoretic security, okay? But then we will also talk about something more. We will talk about models which are weaker, for example, computational models, or models that are even stronger, for example, device independent, or something which is unrelated, which is relativistic models. So I will only be hinting on these three models. I will mostly spend time on the information theoretic, but I will tell you a little bit what's happening in these different security models, okay? Okay, so this is the outline of the talk. We'll start with bit commitment. I will give you a simple protocol. The idea is that you understand a little bit how to construct protocols and how to prove their security. Okay, so there will be some math in the talk. Okay, we'll start by bit commitment. There's coin flipping. There are two variants of coin flipping. They're very different to each other: strong coin flipping and weak coin flipping. This will all be in the information theoretic model. And then I will tell you about how to do this kind of primitives, bit commitment and coin flipping, in the other models. And at the end, we'll talk about more primitives, okay? Okay, so let's start with this. First, I will show you some simple protocol that achieves some cheating, which is not very good from a practical point of view, but it's strictly better than anything you can do classically. And then I will show you how to prove a lower bound using some new relations between trace distance and fidelity that you all know. And I start with this because it uses the math that we all kind of know how to manipulate. Okay, so what is bit commitment? Most of you already know what is bit commitment. For those of you who don't, a bit commitment is a protocol between two parties. Okay, there are two phases in bit commitment. The first one is called the commit phase, and the second one a reveal phase. So what happens in the commit phase? So Alice has a bit, either 0 or 1, and somehow she wants to commit to that bit. Okay, she wants to send something to Bob or have a whole interaction with Bob. Says that at the end, somehow she has committed to this value of x. Okay? What we want is that once this commit phase is over, Bob should not know what x is. Okay? So the protocol where Alice just sends x to Bob, then obviously she has committed to x because she cannot change her mind because she has already revealed x. But this is not a good protocol because Bob knows what x is. So somehow Alice has to commit to this bit. Bob shouldn't know what this bit is about. But somehow in the reveal phase, if Alice wants to reveal a bit, if she was honest, then she can always reveal one of the two values, but she cannot reveal both values at the same time. So think of it in the following way. I can always get a safe, okay, with a key. I can write on an envelope the bit I want, either 0 or 1. I can put the envelope in the safe, and I will send you physically this safe. Now, you don't know how to open the safe, so you don't know anything about what is the value inside the safe. I cannot change my mind because the safe is now with you. And in the reveal phase, I can send you the key. I can send you the key that opens the safe, and then you can open the safe and see what is the value. Okay? So the whole point of bit commitment is trying to do this in an electronic way with communication without having to physically send back and forth these kind of safes. Okay? And this is a very important primitive, and many things that you would want to do in a real network actually are reduced to this kind of primitive. For example, if you want to do zero knowledge, if you want to do identification, you can do it if you have some primitive that does bit commitment. Okay? All right, so more formally, what are the cheating probabilities? How are we going to define the security of this protocol? We're going to look at, we're going to look at two cheating probabilities. The first is the cheating probability for Alice, and what would be this probability? Is the average probability of revealing both 0 and 1. Okay? So already there is a slight change with the classical definition for those of you who know the classical definition. However, this is kind of the only definition for which we know how to prove something. Okay? In any way, so what we're saying is that at the end, during the reveal phase, Alice cannot have high probability of revealing both 0 and 1. Okay? It could be that one of these is 1. If she's honest, for example, and she honestly committed to 0, then the probability that she can reveal 0 will be 1. But in that case, this thing has to be small. Okay? So it's always more than half. The question is, how much more than half is it? If it's 1, then she can fully cheat. If it is very close to half, then she cannot cheat. Okay? And the second cheating probability is the probability that Bob can guess what is the committed value, x, before the reveal phase. So once Alice has committed to this x, what is the probability that Bob can guess what is the value? Okay? Again, it's at least half because it's a bit. I can always guess 0 or 1 with probability half. It will be correct with probability half. The question is, how bigger is this probability of cheating for Bob? Okay? So these are the two cheating parameters that we consider in this standalone version of bit commitment. And we say that the protocol has cheating to be the max of the two probabilities. Okay, usually we'll make these two probabilities the same, so we don't give any advantage to Alice and Bob. So any questions about bit commitment? This is just the definition. Okay. So what is the main idea? The main idea is that the commit phase of this protocol will be a quantum state. There will be a quantum state that corresponds to 0 and a quantum state that corresponds to 1. So honestly, when Alice wants to commit to 0, she will send this quantum state that corresponds to 0. If she wants to commit to 1, she will send the quantum state that corresponds to 1. And what is the properties that we use? The properties that we use is that if you have two quantum states that are not orthogonal, then you cannot always distinguish. So this is where we're going to get some security against Bob, because Alice is going to be sending one out of two non-orthogonal states, which means that Bob will not have a very high probability of distinguishing whether Alice sent the state that corresponds to 0 or the state that corresponds to 1. Okay? On the other hand, since these two states will be different, there is no way Alice can send something that with high probability can be both things at the same time. So Bob is going to make a check. Bob is going to check whether the state that Alice sent is the correct state that corresponds to 0, or that it's the correct state that corresponds to 1. And since these two states are not the same state, no matter which quantum state I send, there will be always some probability of not being correct in one of the two cases. Okay? So this is the other property that we're going to use, that you cannot reveal two quantum states by sending one. Okay? Okay, so here's the protocol. So Alice will create this bipartite state, psi x, which will be just xx plus 2, 2. Okay? X is either 0, 1, depends on the bit that she wants to commit, and 2, 2 is just 2, 2. Okay? So she creates this state. She creates this state and sends the second register to Bob. So what is the state that Bob has? Bob has x with probability half and 2 with probability half. Okay? So I can define rho 0 to be the state that with probability half is 0 and with probability half is 2, and rho 1, which is the state that corresponds to 1, to be 1 with probability half and 2 with probability half. And then what happens in the reveal phase? Well, Alice reveals what is the x she wanted to commit, and she sends the first register that she had kept with herself, she sends it over to Bob as well. And what does Bob do? Bob knows what is the state. If Alice reveals 0, then he knows that the state is supposed to be 0, 0 plus 2, 2. So he will make a measurement 0, 0 plus 2, 2 or orthogonal, and he will accept if he gets the outcome 0, 0 plus 2, 2. Or if it is 1, then the state should be 1, 1 plus 2, 2. And again, he will make a measurement, is it 1, 1 plus 2, 2 or something orthogonal? If he gets the orthogonal thing, it means that Alice has cheated, so he will abort. If he gets the correct thing, then he will accept that, yes, Alice honestly committed to the bit x. Okay? All right, so security. So here is one thing that Bob can do. So what is Bob trying to do? Bob is having a copy. So for now, we're assuming that Alice is honest, Bob is cheating, so Bob is trying to guess the bit x from what Alice has sent to him during the commit phase. So what Bob has is this state. He either has rho 0 or rho 1. And what he needs to do in order to guess x is just try to differentiate between rho 0 and rho 1. Okay? So here is a measurement that he can make, which is measuring the basis 0, 1, 2. So what will happen if I measure in the 0, 1, 2? This is my state. I have, with half probability, I will have rho 0. With half probability, I will have rho 1. In both cases, with half probability, I'm going to get 2. If I get 2, then I have no idea if Alice's committed bit was 0 or 1. Okay? But with half probability, I'm going to get either 0 or 1. In which case, I will know exactly what Alice has committed to. Because if I get a 0, I know that 0 can only come from rho 0. And if I get a 1, I know that 1 can come only from rho 1. Okay? So by doing this measurement, my probability of guessing x will be 3/4. Why? With half probability, I'm getting 2, and then the best thing I can do is just guess if it was a 0 or 1. Okay? And with half probability, I'm going to get either 0 or 1, and then I know exactly what is the committed bit. Okay? So half times 1 plus half times half, it will give you this 3/4 probability. Okay? So what have I showed? I have just showed that there is a cheating strategy for Bob that achieves probability 3/4. Okay? We would want something stronger. We would want that no matter what Bob does, he cannot get the right answer with probability more than 3/4. Okay? So Bob is usually easy because we know what is the optimal measurement to distinguish two quantum states. Okay? It goes back to Hellstrom a long time ago. So if I have two states, rho 0 and rho 1, and I know that I'm getting each one of them with probability half, then I know exactly what is the optimal guessing probability of distinguishing between 0 and 1. This is exactly given by this, which is half plus the trace distance between rho 0 and rho 1 over 2. okay? Okay? And then if you just calculate what is the trace distance between row 0 and row 1, this will be half, I guess, which will make this 3/4. Okay? So what have I shown so far? I have shown that in this protocol, no matter what Bob does, no matter what cheating probability he gets, the best cheating probability will be 3/4. And actually, there is a simple measurement that he can do to actually get this probability 3/4 of cheating. Okay? Okay, so let's go to Alice. So what can Alice do? Alice wants to send some state to maximize the probability that she can reveal 0 and she can reveal 1. So 0 and 1 are two density matrices, row 0 and row 1. Kind of what she will do, it will send something in the middle, so that she will maximize the probability of both revealing 0 and revealing 1. So for example, she can create this state here and send the second register to Bob. Okay? And then if I want to reveal 0, I'll just say it was 0. And what is the probability that Bob is going to accept that Alice reveals 0? Well, it's the probability that this state here is going to collapse on the 0, 0 plus 2, 2 state, right? Because if Bob gets in his measurement 0, 0 plus 2, 2, then he will accept the committed value. And if you just look at the inner product between this and this square, you'll get 3/4. Again, if she wants to commit to 1, then it will be the probability that this projects to the 1, 1 plus 2, 2, it will still be 3/4. Okay? So by sending this state here, which is kind of between the two states that she was supposed to create, she can manage to both reveal 0 and 1 with probability 3/4. Now, there is no nice way to prove that this is the optimal strategy, apart from actually writing down a general strategy, which is I'm creating some state with some amplitudes like this, and then you optimize over the states, and you actually see that this is the best state. Okay? So I don't know of a nicer or more elegant way of proving that this is the best strategy for Alice, apart from actually seeing that it's the optimal by taking the general strategy, then kind of saying that it should be symmetric between 0, 1. It should also not have anything like 3, 4, or 5. It should be on this QCrypt. And once you do all this, then you end up with some parameters, you optimize them, and you see that this is the optimal strategy. Okay? So this is not very interesting on the math side, but you'll get exactly the 3/4 again. Okay. So this is very simple. I gave you a specific protocol, and I told you that you get, for Bob, probability 3/4 of cheating, for Alice, probability 3/4 of cheating. Okay? Any questions on this? This is a simple protocol just to...
Is this one easier to prove that Alice cannot cheat any better? Is it easier to prove with this one than the Iordanis version, which is easier to implement that?
It's the same. It's the same. So I'll actually use Iordanis' protocol. I'm almost calling this one Iordanis' protocol, but it's the same. It's not the same stage, but it's the same protocol. Yes, yes. So there have been quite a few protocols that give you 3/4. I know at least 4 or 5 protocols that they all use different kind of states, but they all give you 3/4 probability. So this is just one of them. But the main idea, the main difference here is that you use this QCrypt. If you use only qubits, like 0 and 1s, then you cannot get so easily the 3/4 probability. So there is a protocol, for example, I create 2 EPR pairs, I send you the 2 halves, and what you do is that you check one by asking me an EPR pair, and you measure the other one.
2 pairs of qubits is bigger than...
That's true. That's true. So yes. So if I'm only on a 2-dimensional 0, 1, and I can only send you one of these things, I don't know how to get better than cos square pi over 8. Okay. So now I want to prove to you a lower bound. So we saw that the optimal would be half and half. No one can cheat, Alice cannot cheat, Bob cannot cheat. What we know so far is that we can have protocols where 3/4 is achievable. So the question would be, how much can we push this 3/4 down and how close to half can we go? Okay. 9:30 we started, right? Okay. Okay, so let's look at any bit commitment protocol. There is a commit phase where Alice starts with X and Bob is supposed to have row X at the end. And then there is a reveal phase where Alice says, my X was 0 or my X was 1. And then there might be some more interaction between Alice and Bob so that Bob can check whether Alice cheated or not. Okay? So I'm going to give you a cheating strategy for Alice that works for any protocol. And I'm also going to give you a cheating strategy for Bob that also works for any protocol. Okay? So what is the cheating strategy for Alice? Well, what would be a general strategy? In the commit phase, Alice is not going to be honest. So at the end, Bob is not going to have either row 0 or row 1, but he's going to have some mixed state Xi. Okay? We don't really know what this Xi is, but let's say that in any cheating strategy of Alice, you will do something, Bob will end up with some state. Okay? Call this state Xi. And then what do we know? We want to know that if we want from the state Xi to reveal that we had 0, then the probability that we can do it is the fidelity square between Xi and row 0. And again, if Alice wants to reveal row 1, it will again be the fidelity square between Xi and row 1. Now, proving the optimal cheating strategy for any protocol that I don't even know what the protocol looks like is obviously not possible, right? If you don't give me a specific protocol, I cannot tell you what would be the optimal cheating strategy. But there is one cheating strategy that you can always do. So what is this cheating strategy? Instead of honestly committing to 0 or honestly committing to 1, what I can always do is go to a superposition of 0 and 1, and then honestly apply the protocol in superposition between 0 and 1. So I can create my qubit 1 over square root 2, 0 plus 1, and control all 0, I honestly run the protocol and for 0, and control the 1, I honestly run the protocol for committing to 1. So what would this do? This would create this state which instead of being row 0, row 1, it will be the average between the two. So I can always create this state half row 0 plus half row 1, okay, which I call rho plus. No matter what protocol you give me, if I can honestly run it for 0 and I can honestly run it for 1, I can also run it on superposition of 0 and 1. Okay? So this is one cheating strategy that Alice can always do. And then this means that the probability, the cheating probability, which is half the probability I reveal 0 plus half the probability I reveal 1, it's exactly this half fidelity squares between row 0, row plus, and row 1, row plus. Yeah? Well, the thing is that this is the state that Bob has. Since I'm keeping the 0 plus 1 on myself, what Bob is going to have is with half probability row 0 with half probability row 1. Okay? Thanks. Okay, so this is a cheating strategy for Alice for any protocol that you can imagine. Let's go to Bob. So here's the cheating strategy for Bob. Bob will honestly follow the commit phase, which means that at the end of the commit phase, he will have either row 0 or row 1. It seems like a bad cheating strategy because he's just honest, but this will be good enough. So Bob will honestly follow the commit phase, and then what he will do is that he will try the best measurement to distinguish between row 0 and row 1. And we know what is this cheating probability is, as we said, half plus the trace distance row 0, row 1 over 2. Again, he can always do this cheating strategy because he can always follow honestly the protocol and then perform the optimal measurement. Okay? So what have we done? We have shown that for any bit commitment protocol, the probability that Alice can cheat is bigger than this, and the probability that Bob can cheat is bigger than this. So what we need is a relation between these two. You can see that the closer rho 0, rho 1 are, the better Alice can cheat, because the fidelities are going to be high. But the closer they are, then the trace distance will be small. So if I make rho 0 and rho 1 very close to each other, then Alice can cheat a lot, Bob can cheat almost not at all. If I make these states almost orthogonal, then Bob can cheat a lot, and Alice cannot cheat at all. So somehow I want to see what happens in between. And here is what we have proven with Andreas Ayew a couple of years ago, is that there is a very simple relation that connects these average fidelity squares with the trace distance. So what does this mean? This means that I can rewrite these two probabilities. The first one is this, which is bigger than this, and the second one as it was before. And now I just have two inequalities on one variable. So I can make these guys equal, and I get this lower bound. So look at this. This is a lower bound of, I'm not going to read this because it's going to take a lot of time. But this is what we get from this very almost trivial analysis of the cheating strategies. Okay? What I'll show you actually, well, what we will see is that this is exactly the correct answer. So the optimal upper bound for bit commitment is precisely this. You can go epsilon close for any epsilon to exactly this number. So it's not that it looks like 739 something. There are many digits here, but it's precisely this. So somehow, with the simple strategies for Alice and Bob, which is Alice just run in superposition the honest protocol, and Bob just do your protocol honestly and try to guess what is the committed bit, will give you exactly the right answer for bit commitment. Okay? Now,
don't you assume that Bob is not measuring? Somehow he's not honestly following, he's honestly following but never measuring.
What I assume is that you follow the unitary protocol during the commit phase, so I'm not measuring. But all I'm saying is that this is not the optimal strategy. I'm just saying that this is the strategy that I'm going to look at, and the optimal will be at least as good as this one, right? So at least Bob can follow honestly the protocol without measuring, and then make the best measurement to distinguish rho 0 and rho 1, okay? There's no reason a priori why this should be the optimal strategy, cheating strategy, but somehow it turns out that you can always have a protocol where this is the honest strategy. Okay, so this has taken much longer, so I think it's more interesting if I skip this proof. So I can actually prove this, and it's 4 lines of manipulation between fidelities and trace distance. So I have to start with the states rho, I create some other states sigma, and I kind of see what happens to the fidelities of these states and to the trace distance of these states. Then I define some other states so that, again, I know what happens with the trace distance and the fidelity. Then 4th set of states, again, I know what happens with the trace distance and the fidelities. And then the only reason I did this is because now I know exactly what is the fidelity of these states. I can write it like this, and since I know how the trace distance behave, I can continue and prove what I want. Okay, sorry for this, but otherwise I'm not going to go through what I wanted. So it's a simple manipulation on fidelities and trace distance. There's nothing very deep here. You start with your states, you manipulate him somehow to be able to prove this technical thing here. Okay? All right. So this is the end of the bit commitment. So what do we know so far? We know how to do protocols with 3/4, and we know that the best protocols cannot be more than 739. So there's not a big gap between 75 and 739, but there's still a gap between the two that we would like to close. Okay, so now we go to coin flipping. No. No, because I'll show you that 739 is the correct value. But on the other hand, I cannot show you a protocol that achieves 739. Okay, so coin flipping. So what is coin flipping? again, a very simple primitive. You have Alice and Bob, they don't trust each other, they want to communicate so that at the end there is a bit C that comes out, and this is a random bit. It should be with half probability 0 with half probability 1. Okay? This is a trivial primitive, it's a very powerful primitive, and both for bit commitment and coin flipping, I didn't say that classically you can have nothing, in the sense that information theoretically there is always a party that wins with probability 1. So anything that you can do quantumly strictly less than probability 1 is strictly better than what you can do classically. Okay? On the other hand, this coin flipping and bit commitment are used all the time classically because you just use computational assumptions. Okay? But information theoretically, they are impossible. Okay, so this is coin flipping. They want to just flip a coin. What is the cheating that we use here? Again, the cheating for Alice will be how much can she bias the coin. So the coin should be half, 0, 1. Alice wants to bias it either towards 0 or towards 1. We calculate what is the maximum between 0 or 1 that she can bias the coin. If this is less than half plus epsilon, then we say that the coin flipping has bias epsilon. Okay? The same for Bob. How well can he bias the coin either towards 0 or towards 1? Okay? If it's less than half plus epsilon, then this epsilon is the bias of the protocol. Okay? So what do we know about coin flipping? Actually, coin flipping, we started talking about coin flipping even before bit commitment. It's not very chronological, my ordering. But in 96, both Myers and Low and Chow, they showed that actually it's impossible to do it perfectly quantumly. So this bias epsilon cannot be 0. Okay? So you need to have some non-zero bias. Now the question was, would this bias be half, so you cannot do anything, or can it be very close to 0 again? So then the first paper that showed that something is possible was by Aharonov, Tashma, Vazirani, and Yao in 2000, when they showed that the bias was 91%. In fact, their protocol was better than 91%, it's cos square pi over 8, but their analysis showed 91. In any case, it was strictly better than 1. Okay? And then, as Gilles was saying, there was Ambenis in 2001 that actually showed that there is a protocol where the cheating cannot be more than 3/4. So we kind of get back to the 3/4 of the bit commitment protocols. Well, and we see that this is not by chance. And what is even more interesting is that Kitaev in 2003, he came and he said that, look, actually you cannot push this down to half. Okay? No matter what you do, the product of the two cheating probabilities will be at least half, which means that each one of the cheating one of the two cheatings will be always more than 1 over square root 2. Okay? And we'll actually see this proof because it's very nice. So what do we know? Again, we know that there is a protocol with 3/4. You cannot get protocols better than 1 over square root 2. So we'll see how to get this, and then we'll see again how to close the gap between the two and find what is the optimal value between the two. Okay. So why do you get an easy protocol for 3/4? Because if you give me a bit commitment protocol, then I can easily give you a coin flipping protocol. How is that? Well, imagine the follow protocol. Alice creates exactly the same state that she created for the bit commitment. Okay, so she commits to a bit X, basically. And then Bob just sends a random bit Y to Alice. And then Alice reveals, as in the bit commitment case, what was X, and Bob checks that it was the correct thing. Okay? So the only difference is this extra message here from Bob to Alice, and the output, the outcome of the coin will be the parity of the two bits, X and Y. So how do I flip a coin? Alice picks X, Bob picks Y, and the parity of the two is my coin. So how do I do it? Well, Alice does not reveal X in the clear, but she commits to this value X. Then Bob reveals what is Y, and then Alice has to reveal X and see what is the parity of the two. So if you look at what is the security, Bob's probability, let's say that Bob wants 0. So what does Bob have to do? He needs to output Y here, which is the same as the X that Alice committed to, which means that he has to guess X from the same committed state as in the bit commitment protocol. And this we know can happen with probability 3/4. Okay? And how can Alice cheat? Well, imagine that Alice wants 0, then she sends some state, and depending on y, which with half probability will be 0, with half probability will be 1, she will have to reveal either 0 or 1 with probability half. So here cheating again is exactly the same as the cheating probability that she had in the bit commitment protocol, and again is 3/4. Okay. Okay, so this was not the most interesting part, the upper bound, but what is very interesting is the lower bound. So how do we prove that coin flipping cannot happen with probability more than 1 over square root 2? And for this, we're going to look at semi-definite programs. So let me start by looking at a general protocol. Okay, so here is a protocol. So I don't know how well you can see this because it's copy-paste from a PDF, but all I'm saying is that there is Alice and there is Bob. There are 3 spaces. There is A, which is the workspace of Alice, M, which is the message space, which is the qubits that go back and forth between Alice and Bob, and B, which is the workspace of Bob. So what is a protocol? A protocol starts with some initial state. Think of the initial state as all zeros. Okay, we start with nothing. And then at every round, someone applies a unitary. Either it's Alice. So Alice applies a unitary in the space A and M. She cannot touch Bob's workspace because this is with Bob. She applies some unitary on A and M and then sends this M part to Bob. Then Bob applies a unitary on M and B, and she sends the M part to Alice, and so forth. They go back and forth. So there are these unitaries. Forget about disease. They're projections. We need them for a technical reason, but it's okay. Think about this as a unitary. I apply a unitary on AM, I send M. I apply a unitary on MB, I send M, and so forth. So this is just a general way of describing any interactive protocol between Alice and Bob. Okay? And what do we know? We know one thing. We know that at the end, if everything is honest, if both Alice and Bob have honestly followed the protocol, then the probability that they measure 0 is half. Meaning that if psi n is the honest state at the end of the protocol, when they measure with their projections that correspond to the outcome 0, then this should be half, and the probability that they will both get 1 should also be half. We're talking about the honest case. In the honest case, the coin flipping protocol should give you 0 with probability half and 1 with probability half. Okay? So this is what we know about the protocol. We start with all zeros, then each one takes turns applying some unitary, and at the end, they both get 0 with probability half, or they both get 1 with probability half. Okay?
Why do we restrict the protocols so that if they're both honest, we do get half and half? It might be that the protocol, which even if they're honest is slightly biased, would be better if they try to cheat.
Sure. So there is nothing very crucial about this half. Whatever I put here, this is what will come up in my lower bound. But let's say that if I want a fair coin, let's start with something that gives me half and half. The lower bound works even if this was something else. It's just that it will change the parameter. Okay? Okay. So then, what do I want to do? I want to see how can Bob cheat. So I'm going to write down a semi-definite program whose value is going to be the cheating probability for Bob. So it's a mouthful, but it's very easy to understand what it says. So what Bob is trying to do is, instead of doing the correct unitaries here, he will do something else. Okay? In any cheating strategy, Alice will follow honestly the protocol, but Bob is not going to perform these unitaries here. He will do something else. So what we're going to write down, we're going to write a program where the variables are the states that Alice has in every round of the protocol. Okay? And what we want to find is, we want to find these states that optimize something. What are we optimizing? We're optimizing the probability that Alice is going to measure 1 on the final state of the protocol. Okay? This would mean that Alice will accept that the coin is 1. So I'm trying to calculate what is the probability that Bob can bias the coin towards 1. And this probability is exactly the probability that at the end of the protocol, we'll have some state rho, and Alice is going to measure 1 on this state. Okay? So my variables are all these states from 0 to n. I'm trying to optimize the probability that this state at the end will make Alice measure 1. But obviously, I cannot put whatever states I want. There are some constraints that come from the fact that this is an interactive protocol and that Alice is honest. So the constraints are very simple. The first constraint says that in the beginning, everything is 0. Okay, or size 0, but imagine that this is 0. So this is just that in the beginning, we start with all zeros. And then, depending on whether it's Alice's turn to apply a unitary or Bob's turn to apply a unitary, we know something. What we know is that if Alice applies a unitary, then it is the correct unitary, which means that the state I minus 1 will give me the state I by applying the correct unitaries that are specified by the protocol. So in a round like this, the change that happens in the state AM is by the honest unitary which is prescribed by the protocol. So this is basically what this thing says. To get the ith state, I just look at the I minus 1 and apply this unitary. And what I also know is that in an even round where Bob is the one who applies a unitary, I know that this part of the state has not changed because Bob has not access to the workspace of Alice. So what I write here is that if you trace out M from the state here, which is this state, then this is exactly the same as it was in the previous round. Bob can do whatever he wants on M and B, but he cannot touch A, which means that this state is the same as this state when you trace out, when you only look at the A part. Okay? So this is the semi-definite program. If we understood this, this is fantastic. So what do I want? I want to optimize the cheating of Bob for 1. I need to find all these rows that maximize this quantity, given that these rows fulfill these constraints. Okay? The reason I did this, okay, so now imagine I want to study a protocol and find what is the cheating probability. Well, this is kind of useless. Why? Because it's a maximization, which means I have to find the best possible rows that give me this probability. So this I have no idea how to do. I don't know how to enumerate overall cheating strategies. But what I can do, okay, this is the same for Alice, but it's not important. But what I can do is I can go to the dual of the semi-definite program. So what is the dual of the semi-definite program? I won't tell you exactly how to derive the dual, but there is a very canonical way of taking a primal and getting the dual. The main idea is that instead of having a maximization here, you now have a minimization. You're now optimizing over this semi-definite, positive semi-definite matrices Z, okay? And the constraints that you have here are basically derived from the primal, okay? So you know that these Z's kind of decrease as matrices the more you go on in the protocol. When it's odd, when it's even, they remain the same. And you know that at the very end is equal to the projection on the 1, which was what was here. So I don't really want you to understand how we get from the primal of the dual, but once I write down a semi-definite program, there is a simple way of writing down what is the dual. So why we wanted to do this? Because now it's easy to prove an upper bound on this cheating probability. If I want to say that the cheating cannot be more than blah, then what I need to find is some solution for these Z's where this guys gives me this thing, right? So I don't need to find the optimal Z. Any Z that I find which is a solution, any Z that I find that corresponds to this, that satisfies these constraints, will give me an upper bound on the cheating probability. Okay? And the hope is that I will find a good solution Z, and then this will give me a tight bound for how much Bob can cheat. Okay, so this is the most delicate part, but you know, all I've done is that I looked at the general protocol where Alice and Bob apply some unitaries, and I wrote down a semi-definite program where I'm optimizing over all possible cheating strategies, and the optimization is the cheating probability of Alice and Bob. This is still a maximization, so I don't know how to maximize over all cheating strategies. So I write the dual. The dual is a minimization. So if I want to show that for a specific protocol, the cheating cannot be more than 3/4, I just need to find a single solution of the Z's that will give me that this is 3/4. And then I know that it cannot be more than 3/4. It could even be less, but at least it's not more than 3/4. Okay, So once we have mastered the primal and the dual, now we can very easily get the lower bound for strong coin flipping. So here I just rewrote the dual, and I rewrote this thing that we know that the projection on the ones in the honest case is half. Doesn't have to be half, but let's say it's half. Okay? So then the lower bound is basically 2 lines. So I rewrote what is the probability of cheating for Alice and the probability of cheating for Bob. This guy here is exactly, I'm rewriting the trace in a nice form. So you take the initial state psi 0, you wrote the z0 here, and you have identities on the other part. And you also have PB, which is this. So this is basically what you are optimizing in the dual. And here is the entire proof. I look at the product of these 2 probabilities. The product of the 2 probabilities is basically this times this, the product of these 2. But note that this psi 0 is a product state, so I can kind of combine these 2 z's, both on A and on B, and I can write it like this. So I have the state psi 0, and now I apply ZA0 here and ZB0 here. Okay? Why can I do this? Only because this psi 0 is a product state. Otherwise, it's not possible to say that the product of these 2 is actually this. Okay? But I can do it. I can write it like this. And then all I have to do is to say that this guy is bigger than the last one on n. Why? Because I use these constraints here. These constraints exactly let me go from the psi 0 and z0 to the psi n and zn. Okay? The reason that this is bigger than 1, bigger than 2, bigger than 3, bigger than n is exactly because of these constraints. And once I'm here, I know what is the zn and zbn. They're just the projections. So I put them here, and this thing, I know what it is. It is the honest probability of getting 1. So this is half. It doesn't have to be half. It could be whatever. What I get is that the product of the 2 cheating probabilities for Alice and Bob is at least the honest probability of outputting 1, which in this case is half. Okay? So for bit commitment, we used some very simple things to get the lower bound, which is trace distance and fidelity. For coin flipping, to get a tight lower bound, you actually, the only way we know how to do it is by going through the semi-definite programming. But the semi-definite programming is a very powerful kind of tool, and it's really nice to see. So even though these primitives may not be very useful in practice, I mean, the math that goes into proving what is the right bounds is quite beautiful. Okay, so any questions about this? It was a little fast, but you take a protocol, we write it in an SDB, you go to the dual, and then you just show that the product of the probabilities, according to the constraints of the dual, should be more than half. Okay, so this is the whole proof. Okay, so let's recap. What do we know? We showed upper bounds of 3/4, and we showed lower bounds of 1 over square root 2 for coin flipping, and the 739 for bit commitment. So again, we're not done. We need to basically close this gap and close this gap. So that's 30, 50 minutes. I have half an hour. Okay. So the way to close this gap is the following. So basically for quite some time, people were trying to understand if the right value here is 1 over square root 2 or 3/4. And basically, whatever new protocol you would come up with, it will still give you 3/4. It will still give you 3/4. It will still give you 3/4. On the other hand, the lower bound is brilliant, so the math that goes into it. So there was also a reason to believe that the 1 over square root 2 was the right answer. So what do we do when we don't know how to answer a question? We basically change the question. So we didn't know what to do about strong coin flipping. So the idea was that, okay, maybe let's look at a weaker primitive, which we call weak coin flipping. From a practical point of view, actually, it's what you would imagine you need in practice. Okay, so when Blum kind of defined coin flipping, when he gave the example about Alice and Bob getting a divorce and who's going to get the car, actually what you do is you flip a weak coin. You don't flip a strong coin. But anyways, what happened is that Mochon in 2006 and then 2007, he defined this weaker version of coin flipping, and he actually showed that you can almost perfectly do it. So here is a primitive which is not called QKD, but you can have almost perfect information theoretic security. Okay? And then, yeah, it took us 7 years to understand the paper, go from 80 pages to 40 pages. So we wrote some proof. It's a little simpler to understand that it works now, but still we don't really understand much. And I'll tell you the parts that we don't understand. Okay? But there are some very beautiful techniques that come from Kitaev's formulation through the semi-definite programming that Mochon took even further. There are many reasons we like weak coin flipping. One is that you can actually do it with almost perfect security. So not many things you can do with almost perfect security. The second thing is that once you have this weak coin flipping primitive, this will actually give you the optimal bound for strong coin flipping and the optimal protocol for bit commitment. So the thing that was missing to go from 3/4 to 1 over square root 2 or from 739 to 3/4 was precisely this weak coin flipping thing. Once I give you this box that does weak coin flipping, then you can get the optimal bounds both for coin flipping and for bit commitment, and it was actually the lower bounds that were the correct answers. So the 3/4 is the one that was not good enough. Okay, the other interesting thing about weak coin flipping is that we have a protocol, we can prove that it has arbitrarily small bias, and we have no idea what the protocol looks like. So there is a lot to be done here, and yeah, there is a lot to be done here. Okay, so what is weak coin flipping? What is weak with respect to the strong coin flipping? So the main idea is that in the strong coin flipping, we said what? We said that we don't want Alice to bias the coin neither towards 0 nor towards 1. So we wanted both the probabilities that she can make it 0 or 1 to be small. And the same for Bob. We really wanted this coin to be a random coin at the end. In the weak coin, we don't care that the coin is random because in some sense we know what Alice wants and what Bob wants. So Alice wants to get 0 and Bob wants to get 1, right? Alice wants the car or Bob wants the car. So I have this extra assumption here that Alice wants 0, Bob wants 1. And then what I care about is that Alice cannot win with very high probability and Bob cannot win with very high probability. It could be, though, that Alice wants to lose and then she can perfectly and always lose. Okay? So that's why the difference is that here Alice cannot bias the coin neither towards 0 nor towards 1. Here we only care about one of the two values, which is the value that corresponds to her winning. Okay? So Alice cannot bias the coin towards 0 and Bob cannot bias the coin towards 1. So this is why it's a weaker version of coin flipping, because at the end it's not necessarily an unbiased coin because Alice or Bob can decide to lose and give what Bob wants. Okay? Having said that, this is basically corresponds to any kind of zero-sum game that two players play in a network. So any kind of decision that two players have to decide, for example, if I want to sign a contract online, someone has to sign it first. So who has to sign the contract first? You can flip a coin. You don't need the random bit. You know that both players want to sign second. So something like this is useful enough for many of the things that we use coin flipping for. Okay? Okay, so this is the definition of weak coin flipping. So I showed you how to go from a protocol to the semi-definite programs. Okay? And then you go to the duals and you have the Z parameters there, which were the solutions to the dual program. So what the brilliant thing that Kitaev and Mochon did is to say that, okay, I'm going to give you a completely different model, and I'm going to show you that if you can show something in this model, then this will provide you a protocol for weak coin flipping and also a security proof that the bias cannot be more than something. And what this model looks like is basically points in a two-dimensional space going around. So you start with 2 points, then you can split 1 point into more points, then you can move some point up, then you can take 2 points and merge them, then you merge them, and then you end up somewhere. So you don't need to understand because it's not obvious, but the idea is that if I show you something like this with a final point here that has some coordinates u and 1 over 2u, let's say, this basically corresponds to how much Alice can cheat, and this corresponds to how much Bob can cheat. So what I showed you here is a 1 over square root 2 protocol of Speckens and Rudolph for weak coin flipping, for example. It's just simple. The moment I showed you this, not only do you have a protocol, you also have a proof that the bias of the protocol is exactly these cheating probabilities. Okay? So what do we need to understand from this? We need to understand what do these points mean, okay? And how can I go from some point to some other points, okay? So I only have one slide. So I want to show you that basically what these point games are is a graphical representation of these dual solutions, okay? So the way you will go to something that looks like this is by looking at the dual solution. The dual solution is the z's that we said, okay? We have some constraints about the z's, and we know that the probability of cheating is basically the projection of the initial state on the z0, okay? So what will be the quantity that we look at? Again, we said that we need to join the two cheatings together. This is exactly what we did for the lower bound for the strong coin flipping as well, okay? So what we really look at is this quantity. At round I, what is the projection of the honest state psi I onto this operator here, where this is the ZAI and this is the ZBI, okay? We have no idea what this thing looks like, but this is what we are trying to graphically represent. What do I mean by that? I mean that if I have a point here, I look at the two coordinates of the point. The coordinates of the points are nothing more than some eigenvalues of these matrices, okay? So this corresponds to an eigenvalue of this, and the ZBI corresponds to an eigenvalue of this. So the only possible points are pairs of eigenvalues of these matrices. And what is the weight? What does the weight correspond on the points? It corresponds to the projection of the honest states onto the eigenvectors that correspond to these eigenvalues. So I have these eigenvalues ZAI and ZBI. There is some eigenvector, some eigenspace that corresponds to these eigenvalues. I look at the projection of the honest state on this thing here. This is the weight that I give to the point. Again, this is a very, very high level description, and I don't want you to understand much. I just want to show that if you start from these dual feasible points, these z's, there is a way to kind of see how they change in time from round to round by looking at the eigenvalues and the projections of the honest states into the corresponding eigenspaces. And there is one more thing that I need to define these kind of games is how do I take a point and I move it to some other point? Or how do I take a point and I split it into 2 points or things like that? And the legal moves that you have basically come from the constraints on the z's. You had some constraints on the z's. These are the constraints of the dual SDP. You look at these constraints and basically they tell you what kind of transitions you can make in these points. I just wanted you to get an idea that there is some very interesting math happening in all this. It's not obvious what I'm trying to say because it's just not obvious, neither to me, okay? But the idea is that I want to prove an equivalence between having a weak coin flipping protocol and having these point games, these points going around, okay? And I start with the protocol and the cheating strategies. I write down the semi-definite programming. I look at the dual of the semi-definite programming. And then to show the equivalence between these games, I have to look at the topology of infinite dimensional convex cones. I have to look at dual of these cones, dual of these cones. I have to look at operator monitor functions. So this is all the mathematics that Muchon was kind of using and we kind of simplified. And by doing all these things, you prove that if you give me a point game that satisfies these constraints, then you already know that a coin flipping protocol exists. So even if you don't understand how this equivalence proof works, you can still play with these point games. Okay? And what Mochon also did is that he actually showed a point game, which is a valid point game because it satisfies all these constraints, where the last point here, which will tell me what is the bias for Alice and Bob, is exactly the point half plus epsilon, half plus epsilon. So there are two main parts in this work. The first part says that if you want a protocol and a proof of security of the protocol, give me a point game whose final point will tell you what is the cheating probabilities. So this is all the math that goes into here. And the second part is to say, here is a point game. It's valid because it follows the rules. And look at the final point, is exactly half plus epsilon, half plus epsilon. So this already proves to you that there exists a point game with this cheating.
Do you have to choose epsilon to start with in order to start the move? When you do that converge closer to half, you have to decide ahead of time how close you want to go.
So this, how close to half you can go depends on how long your protocol is and how many qubits you're going to use.
You have to decide from the start.
Yes. So if you want to be epsilon close to the half, then I will give you a protocol that achieves this epsilon. Now, Mochon did not have a calculation on how big the size of the protocol is depending on the epsilon. So it could be that to get epsilon, you need the doubly exponential or triple exponential rounds. So we calculated the rounds, and we can prove that it should be at most exponential, but maybe it's better, but we don't know actually. Okay, so as I said, I have 15 minutes, no? Okay, so this is how to go from weak coin flipping to strong coin flipping, but I'm going to skip this part. It's a very simple thing. Okay, maybe let me just say one thing. If I give you a box that does weak coin flipping, then there is a trivial way of trying to flip a strong coin. The trivial way would be, let's flip a weak coin flipping. If you win, then you tell me what is the output of the coin. If I win, then I will tell you what the output of the coin is. So if you use this weak coin flipping in this way, you get exactly a protocol with 3/4 probability of cheating. So yet again, we were stuck at this 3/4. But then what you can see is that, well, you can do a little bit less trivial things with this weak coin flipping, which is that instead of just performing the weak coin flipping and then whoever wins chooses the game, I'm going to have Alice say, if I win, then I'm already telling you that the outcome of the coin will be A. And I say that before we actually flip the weak coin. Then we flip the coin, and then if Alice wins, then this is the outcome of the coin. She has already declared it. If Bob wins, then with some probability it's going to be A, with some probability it's going to be the complement. You have to play with this parameter P, and also we perform a weak coin flipping here, which is not half-half probability, but Alice wins with higher probability than Bob. Once you fix the Z and the P, you do some calculations, and you get exactly the optimal protocol, 1/√2. But this is very simple. The protocol is just this, and the analysis is 5 lines of classical probabilities, right? So I only use this as a black box, and once you give me this black box, I just give you the 1/√2 upper bound. Sorry. In the clear, in the clear. Everything is classical. Apart from this box, everything is classical here. Okay, so I skipped this. Okay, but now we are done in the sense that we looked at coin flipping, the 2 versions of coin flipping, and at bit commitment, and now we know exactly what are the right bounds. It's 1/√2 for coin flipping. This is from Kitaev. This is the protocol from Sheyu and myself that uses the weak coin. For bit commitment, it was 739. We can also show that using weak coins, but in a quantum way now, so it's a quantum protocol, you get 739. And for weak coin flipping, it's half and half plus epsilon. I removed some epsilons here, which is this epsilon. If it's a semi-definite? No. Because the only thing you write down is exactly the constraints that you get from a protocol. The only constraint I wrote down is the fact that Bob, when he's cheating, cannot change Alice's workspace. And that's all. Right? So it's the most general SDP that will give you the max cheating probability. So I'm not losing something there. Okay. So I have 10 more minutes. Fantastic. So implementations. So let's try to implement some of this. So what would be the first thing we would like to implement? Weak coins. Why? Because they have almost perfect security. Bad news, we don't know how the protocol looks like. It has exponential number of rounds. It has logarithmic number of qubits, but we don't really know what happens with these qubits. In any case, we have no idea how to implement this. So this is one of the main questions. Can we get simpler protocols for weak coins? Weak coins mean any kind of two-player zero-sum game, and can we implement these things? Okay? This will go even further than just implementing QKD. What we can implement is strong coins and bit commitment. So the good news is that we can implement them. The bad news is that the security that we get is very weak. I'm telling you that you cannot cheat with probability more than 75%. You cannot sell this to anyone, right? The security should be almost perfect. However, what we can do is that we can put the security on top of any other security that you want. You can take your favorite classical RSA scheme that commits bits. I can give you a scheme that has both securities on top of each other. So if you cannot factor, then you cannot cheat at all. If you can factor, you can still not get everything, but you will have 75% probability of cheating. So this kind of security can be on top of whatever other security, much better security you can think of. Okay, so let's try to see how do we implement this protocol. So let's do bit commitment. It's trivial, right? I create the state XX plus 22, and then when I reveal X, and Bob checks. So you go to the experimentalist and you say, here is a trivial protocol. You just have to create this state, send the second part to Bob, keep the first part, and then 1 month later when you want to reveal, your qubit will still be there, and then you can send it, and then Bob will measure. You know what the experimentalist will say. Go back and do it yourself. So we have to change. So what is the first problem? We have no memories, which means that we have to do something at the same time. Which means Alice should not be keeping anything, should be just sending something to Bob. This is not very difficult. Instead of sending this XX plus 22, I can send these states X plus 2 or X minus 2 with probability half. Bob gets the same density matrix. I got something good here. So at least Alice doesn't need the memory. She needs to create this QCrypt and send it over. Still, Bob needs memory because Bob needs to wait until the reveal phase until he actually checks whether the state was the correct one or not. Bob doesn't have memory, he cannot wait. So what we do is that Bob will guess what should have been the correct checking that he would have done here, and he performs it here. With some probability, he will still be correct, which means that I'm increasing a little bit the bias, but at least now neither Alice nor Bob need memory. So we're getting closer. So we have something now that doesn't need memory. Next problem, losses. So imagine things get lost, and apparently almost everything gets lost. So what do you do with losses? Here is the problem with this thing. The state that Alice sends is either 0 plus minus 2 or 1 plus minus 2. So what would be a trivial cheating strategy for Bob that always manages to cheat? I get the qubit from QCrypt from Alice. I measure in the 0, 1, 2 bases. If I get 0 or 1, fantastic. I know exactly what is the committed bit. If I get 2, I don't know anything. What do? I say that I lost it. So what will happen? Alice will send another QCrypt. I make the measurement I get 0, 1, fantastic. I get 2, oops, I lost it. At some point, actually with probability half, I'm going to get what I want. So if I say 3 times I lost it, then I will always get either 0 or 1 with very high probability, so I will always be able to cheat. So there is a problem with this protocol. What is the problem? The problem is that you have an unambiguous distinguishing measurement. Okay? Why is that? Because this guy here will tell you exactly what is the committed bit. So this protocol is not good if you have any amount of losses. So we need to change it even further. So instead of using the 0, 1, 2 stage, we have to go back to the two-dimensional case. I can only use 0 and 1s. What I do is that depending on x, I put some different amplitudes in the 0, 1. I lost even more of my bias, but okay. I mean, it was already bad to start with. But now you don't have a measurement that will tell you with certainty that it's either 0 or 1. So now you cannot use the losses to gain more information than you could. So this we can actually implement. No, we have more things. So what do we say here? That Bob can check. What is Bob checking? Bob picks one of two bases and makes a measurement. Yeah, but imagine Bob's detector that only clicks in one of the two bases, but not in the other bases. Now this means that basically Bob doesn't pick himself the bases to check, but it's Alice the one that picks the bases. Which means that Alice can cheat perfectly now. So you really have to care even more, you have to symmetrize your detectors. You symmetrize your detectors, of course there are more problems. So once you list down whatever you could think of, you can actually try to implement this. There was a first implementation by Gilles and people in Canada. We did another implementation last year where we did it for 15 kilometers, and this is the classical line, and this is the quantum line, and it's below, which means the bias is less. If you want to read what is the bias, here is 95%, here is 92%. Having said that, it's the first time, these kind of experiments are the first time where you can show that quantum mechanics can do something strictly better than classically in the case where the parties do not trust each other. So we're not doing QKD, we're not doing Bell inequalities, we have two parties that don't trust each other. Still, quantum mechanics can enable for some sort of security which is strictly not possible in the classical case. Okay? Okay. No, you count the detector errors, the detector efficiency, everything is inside. Yeah. So there is a parameter eta, which is the parameter that Alice wanted to send 0 and Bob measured 1. This could happen because the source might not be correct, or because the detector clicked differently, or the dark counts of the detector. So I had to learn all this jargon that I had no idea about, but once you deal with all the experimental things, you can still prove that something works. Yeah. Okay, and this was done in Paris. So I have 2 minutes. There were questions, so 3 minutes. Okay, thanks. Okay, so now I want to very, very briefly go beyond or elsewhere from information theoretic security and see what happens with these primitives, bit commitment, coin flipping in other security models. So to the steering committee, I think there should be a tutorial about this for next time. So please make a tutorial about this. I'm only going to show one slide. So device independence. We saw yesterday that we can sort of do device independent QKD, at least in theory. Even most probably now in practice, we have these loophole-free kind of experiments. So the question is, can we do device independent anything in the distrustful model? Okay. Again, the way you do device independent is that you have Alice and Bob, they trust each other, they play this CHSH game, and they calculate together how well they won this game, they violate some Bell inequality, and everyone is happy. But now Alice and Bob do not trust each other. So the question is, can non-locality actually be helpful in doing device independent here? And we had a paper a couple of years ago with people from Belgium and from Paris, and we saw that, yes, you can use the GHZ game. Okay, we don't know how to use the CHSH. We only managed to do it with the GHZ game. But somehow you can use this game. You know that quantumly you can win it with probability 1. Classically, you can win it with probability 3/4. And you can have a very simple protocol which basically says Alice puts her bit here, she gets out something, and then she sends a classical message to Bob. And then Bob, when he wants to check after the reveal phase, he puts some inputs, he gets the outputs, and then he checks whether the GHZ game wins or not. Okay? So again, we can use this GHZ game or some sort of Bell inequality, and we can show that at least something is possible. Okay, so you can do bit commitment. Okay, in the information theoretic security, it was already 3/4. Here it's like 85%. Actually, I'll show you how much it is. So you can show that Alice can cheat with cosine square pi over 8 because the proof reduces to a CHSH game, and you can show that Bob can cheat with 3/4. Okay. Now, computational assumptions. So we had information theoretic security, we had device independent. Let's go to computational assumptions. So classically, we can make many different computational assumptions. We can have all the things about factoring and discrete log. We can do lattice problems, which is what we called yesterday post-quantum. I still think they are our friends, the post-quantum people, because their claim to fame is that quantum computers will exist, so we are with them on that. We can do hardware assumptions, okay? We don't know how to base cryptography on NP-hard problems. So what kind of quantum assumptions can we do? Can we just use lattice problems? Can we solve quantumly lattice problems or not? This is, for me, one of the most important questions in quantum crypto today. Can we base cryptography on QMA? Why not? Can we have some hardware assumptions like one-time memories? One other assumption is noisy storage. Noisy storage is useless classically because you can store whatever you want. But quantumly, you can say that if I put the state in a quantum memory, then after a while it will deteriorate. So can I use this fact to do cryptography? Well, yes. The main idea is that Alice sends many BB84 states, and Bob can only cheat if he keeps these things in memory for a long time and then perform a measurement. But since his memory is defective, then he has to measure right away. And if he measures right away, then he cannot cheat. So this is the main idea about noisy storage. They can use noisy storage to do bit commitment, oblivious transfer, and all these things. And you can actually implement it because the only thing you do is send BB84 states. So I forgot to tell you that our coin flipping protocol was also just doing BB84 states. So the only thing we kind of know how to do in the lab is BB84 states. So, okay, I take this back. For cryptographic primitives, in the distrustful thing, the only thing we kind of know how to do is BB84 states. Okay. So noisy storage is good because it's almost perfect security. On the other hand, to me, there's always the question, why is my memory bad? But on the same time, I cannot use a classical thing that factors, because if my memory is bad, then my quantum computer is even worse. However, you use noisy memory if you want to do something for the next 50 years, because if you do noisy storage now, then your security is guaranteed even in 50 years that you can maybe factor, right? So one of the reasons to use noisy storage could be that you want something to stay secure in the long run. Okay, very nice talk on Friday on relativistic protocols. Relativistic protocols, yeah, I don't have time to talk about it, but they're cool, they're also implementable. They're classical protocols at the end. You have no quantum there. You just have Alice and Bob here and Alice and Bob somewhere far. And by using the fact that messages cannot go faster than the speed of light, you can actually do bit commitment. It used to be that you can do bit commitment for 1 millisecond, which in sometimes it's okay, but now you can actually do much better than that. So it could be that really relativistic protocols are implementable because everything is classical, and you can have some security guarantees which are good enough to use in practice. The bad thing is that you need to have 2 players who are both here and both there. So somehow if we are both at the same place, we can also, you know, flip a coin or something. But it's very interesting stuff. Okay, 1 minute, last slide. I talked about bit commitment and coin flipping. There is one primitive which is kind of even more important, which is oblivious transfer. Why is oblivious transfer more important? Because it's a universal primitive. Anything you can imagine you want to do, you can reduce it to oblivious transfer. So if we know how to do oblivious transfer, then with some composability questions, we know what happens afterwards. So why is this interesting? Because we don't know the optimal bounds in the information theoretic model. We know the optimal bounds for some weaker version of OT. It's still open. What is the optimal bound in the information theoretic? It's kind of the last one we should know. We don't know if you can do device independent with any kind of security. We don't know if you can do relativistic protocols, relativistic OT protocol. We do know how to do noisy storage. That's fine. The question is, can we say something about oblivious transfer in these other models? Okay? There is a bunch of other primitives. You can talk to me afterwards. And I finish on the dot. So some open problems. There is one more philosophical question, which is, why is it that quantum mechanics allow for coin flipping with probability 1 over square root 2, and with bit commitment with a probability that you cannot even write down succinctly? So why is it, and this goes back to the question, can we talk about quantum mechanics from an information point of view? Like, why is it that QKD is possible, coin flipping is somewhat possible, weak coin flipping is almost possible? What does this tell us about quantum mechanics? The second will be really understanding weak coin flipping and seeing if we can actually implement it. Oblivious transfer, as I said. Will any of these protocols be deployed in practice? Possibly. I don't know if in 10 years we are doing QKD with drones, why not do something like this as well? And then we want to, so these were more peer-to-peer protocols in a network. We can think of many multi-party protocols as well. And there are many other primitives that get into this model of networks where people don't trust each other. Okay, so I'm 1 minute late, so I stop here. Thanks.